4.2 is a section that doesn't really introduce anything new, just gives you a different way of looking at things you've already been doing. So how to solve a quadratic equation graphically. Let's say we're given the equation x squared equals 2x plus 15. It's obviously a quadratic equation, and pretty much regardless of the way we're going to solve it, we would bring everything over to one side. So let's do that. Let's bring the two terms over to the left-hand side and have x squared minus 2x minus 15 equals 0. Now, obviously there's a few ways you can proceed here. You can try factoring it. It does factor. You can complete the square. You can use quadratic formula. You can plug it into quad on your calculator. Let's try graphing it. So what are we actually going to graph? We're going to graph the function y equals x squared minus 2x minus 15. In other words, the expression on the left. And what we're really going to be doing is solving the equation y equals 0. In other words, we're going to be looking for the zeros. And the zeros of a function are the values of x that make y equal to 0. And on the graph, those correspond perfectly to the x-intercepts. So graphically, we're going to look for the x-intercepts. So I've got a graph here created using Desmos of the function. This is the function y equals x squared minus 2x minus 15. And you can see one point very easy to identify is the y-intercept. That's at 0, minus 15. And that should be an obvious point. Let's just take a look at the x-intercepts. We've got an x-intercept there, which looks to be pretty much exactly at -3. And we've got another x-intercept here, which looks to be pretty much exactly 5. There's another point you can figure out just by looking at the graph, and that's the vertex. And the vertex looks to be exactly 1, comma, -16. Now, that x-coordinate of the vertex 1, notice, is exactly halfway in between the two zeros, the two x-intercepts, -3 and 5. You can always take advantage of the symmetry of a parabola and figure out where the vertex is if you can identify the two zeros, the two x-intercepts, or for that matter, any 2 points that have the same y-coordinate. So if you could identify 2 points that had a y-coordinate of 5, that would be fine too. The vertex is going to be exactly halfway in between, horizontally. Now, let's just go back to the original equation we had, which was x squared minus 2x minus 15 equals 0. That's the equation we're really solving here. And as I said, it does factor. You can factor this as x plus 3, x minus 5 equal to 0. And there's a direct relationship, a one-to-one relationship between a factor and a 0. And we're going to see it right here. When we factor a quadratic, the whole point is to take advantage of the product principle, which is that if you have a product equal to 0, then one of the factors is equal to 0, or the other factor is equal to 0. So either x plus 3 is equal to 0, or x minus 5 is equal to 0. If x plus 3 is equal to 0, then x is equal to -3. And that's indeed the 0 on the left-hand side. If x minus 5 is equal to 0, that means that x is equal to 5. Now, there's essentially 3 terms that get used interchangeably or synonymously here, and we've already been using the term 0 and x-intercept synonymously, and now we're going to add one more. We're going to add roots. So the reason why all 3 of these get used interchangeably is because the zeros of this equation are the roots of the equation, and the roots of this particular equation correspond to the x-intercepts of the graph. So they all have a slightly different meaning in a different context, but those 3 terms do end up getting tossed around and used interchangeably. Now, let's go a little bit further. Let's imagine that you didn't factor this, or you couldn't factor it, and instead you used the quadratic formula. So x is equal to minus b. B is -2, so minus b would be +2, plus or minus the square root of b squared, that's 4, minus 4ac, because c is negative, this becomes plus 4 times 15, which is 60, all over 2a, which is just 2. Simplifying, 4 plus 60 is 64, square root of 64 is 8, we get 2 plus or minus 8 all over 2, and this is just 1 plus or minus 4. Now, 1 minus 4 is negative 3, and 1 plus 4 is 5, so obviously we get the same two values. But I want to just take a look at it the way it's written, 1 plus or minus 4. Now, 1 is the coordinate of the vertex. It's the x-coordinate of the vertex. This is the line of symmetry. It's x equal to 1. And if you can imagine adding 4 to that, you get positive 5. If you subtract 4 from that, you get negative 3. And so you can use this as a different way to interpret the number of roots you get for a quadratic equation depending on the value of the discriminant. Because what is 4? What does 4 really represent? Well, 4 was the square root of the discriminant divided by 2. And so, again, if we have the discriminant bigger than 0, we know that that means there are 2 distinct real roots. And you can think of this as one of two scenarios. You either have a parabola facing up and crossing in two places, or you have a parabola facing down and it crosses the x-axis in two places, so you get your two distinct real roots. And if you have a discriminant equal to 0, then again, imagine the quadratic formula. You have a value that corresponds to the x-coordinates, the x-coordinate of the vertex, plus or minus 0. Well, it's not going to change anything if you add or subtract 0, so you only get one distinct real root. And that corresponds to a parabola coming down and just touching the x-axis, or alternatively, if it's facing down, it just comes up and touches the x-axis in one place. And then finally, if we have a discriminant that's negative, the square root of the discriminant would not be a real number at all, and this would correspond to no real roots. Graphically, what that means is you have a parabola that is entirely above the x-axis, never touches it, or alternatively entirely below the x-axis, never touches it. Now, taking this a step further, can we make sense of an equation like y equals ax squared plus c? So this is a quadratic function with no x term. The x term kind of complicates things. So to keep things simple, we'll just examine y equals ax squared plus c. Now, let's think about possible values for a and c in generalities. A could be either positive or negative. If a is 0, we don't really have a quadratic at all, and the graph's not going to be a parabola. So we'll ignore that possibility. So a is either positive or negative, and we'll consider both possibilities. And how about c? Well, again, c could be positive or negative, and 0 too. There's nothing wrong with c being 0. So let's consider those three possibilities. C is positive, c is 0, and c is negative. Now, what kind of parabolas do we get? Well, we've got 6 different options here. A is positive, and the 3 different possibilities for c, or A is negative, and the 3 different possibilities for c. Now, what do A and c really tell us? If A is positive, it tells us that the parabola is facing up. All right, so all 3 along the top, we have a parabola facing up. And c, well, what does that tell us? That's really the shortcut for finding the y-intercept. So c is positive just tells you you have a y-intercept that's positive. And so you end up with a graph that looks like this. And clearly that doesn't touch the x-axis at all, and so you're not going to get any real roots there. C equals 0 means the y-intercept is 0, and in fact this would pass right through the origin. And C is negative means it has to dip all the way below the x-axis and then cross the y-axis below the origin, and so you would get 2 real roots there. The only difference now with A being negative is that the parabolas are flipped. But if C is positive, that means it has to come up above the x-axis and go back down again. And so again, you're going to get 2 places where it crosses the x-axis. If C is 0, it's going to come up, touch the x-axis, and go back down again. And if C is negative, it's going to be entirely below the x-axis. So we have these 6 different situations depending on the sign of A or C. And in 2 of them, we get no real roots. So no real roots in this first one, and no real roots in this last one. We get 1 real root in the 2 middle options. And we get 2 real roots in these 2 remaining options. Now, as I said, when you throw in that middle term, bx, it confuses the matter, and it's probably better just to take it on a case-by-case basis then. But if there's no x term, you can pretty much figure out how many roots you're going to have based on the sign of the coefficients of A and C.